In this video, we're going to show how to accurately write and record the location of electrons in a particular element. On this screen here, do not attempt to write all this down. These are things that we can kind of come back to and sort of summarize. Some big things to think about. There are obviously levels within an element. So we talk about the levels that electrons can reside in. There are also areas. So we're going to think of levels or layers. And the orbitals we want to think of as areas. And then finally, how many electrons can reside in a particular orbital or area, or even back up a little bit, a layer or level. Again, if you want to write these down, you can. For now, this is not something I'm going to specifically quiz you over these numbers. But they are numbers that you do need to be able to know how to use. And again, as we work through this, this ties definitely into the end of section 2, where we talked about quantum numbers. All right, first of all, before we actually start writing these, a couple rules that you just have to sort of pay attention to. These aren't definitions of things that we need to know, but they're sort of rules to apply as we write these. First one's called Aufbau's principle. So basically, we just want to put the electrons in the lowest levels possible. We fill up the electron levels closest to the nucleus, and then we work our way out. Now, when we get to the D's and F's, they do cause a pattern change, so we'll talk about that. Pauli exclusion principle. Basically, no two electrons can have the same set of quantum numbers. So basically, no two electrons can have the exact same address. And again, we kind of talked about in that section 2. Hund's rule. Basically, a simple way to say this, electrons don't pair up until they have to. If we just think of this quote, as we start diagramming these, it will make more sense when we see specific situations. So we want to use these three, kind of have these three statements in the back of our mind as we work through the different examples of electrons. All right, now, before we get to specific elements and learning exactly what we should write for carbon and oxygen and nitrogen and so on, basically I want to talk about three different ways that we're going to sort of write the electron locations. So these so-called addresses. So again, this is not a specific element. I just want you to recognize whenever we say electron configuration, what we basically have is a format where we write names and letters and numbers, and then exponents on those letters and numbers correspond to how many electrons are in that particular element or that particular atom. And again, the sum of all the exponents should equal the total number of electrons, and again, may or may not equal protons. So again, if you see that written this format, then we just know we're talking about writing it the electron configuration way. The next one is what's called orbital notation. Now, the only difference here is instead of writing them as exponents, what we're going to do is we're going to use arrows. So we see here we write a line sort of representing the pocket with a 1s under it. There are two arrows representing there are two electrons in that spot. So as we can see here, two electrons in 1s, two electrons in 1s, two electrons in 2s, two electrons in 2s, four electrons in the 2p orbital, four electrons in the 2p orbital. Now you ask, wait, why didn't I put the two together? Well, go back to the first three rules that we just looked at. Which one of those three described electrons don't pair up until they have to? They spread out. And again, we'll look at more detail of this in specific elements in a little bit. So again, if you see the phrase orbital notation, we know we're writing them in this arrow format. Sort of tied into both of these things, or sort of moving on to the next one, is what do we call the highest occupied level? There's electrons all over the place. But sometimes we don't care about all the electrons. We only care about the highest occupied level. The reason we care about the highest occupied level, these are the ones that are involved in reactions, and they're the ones that are involved in the bonding. So we care about them more than the others. Now, What do we mean by highest occupied level? That means the highest main level electrons are in are being filled. We're talking about the outermost shells or the outermost layers, often referred to them as valence electrons. Well, if those are the outer electrons, then all the other electrons are referred to as inner shell. We do not spend a lot of time talking about them once we get into reactions, because if they're in the inner shell, they're really not going to get involved in the bonding. Just two examples here. I have the element vanadium and the element germanium. And we can see here, this format here is electron configuration. So if we look at this and identify what's the highest occupied level, okay, how many outer shell electrons or how many valence shell electrons are there? Well, if we look here at vanadium, the highest occupied level is 4. We don't want to get any more specific than that. We want to be very general. Level 4. How many electrons are in level 4? 2. So, what's the highest occupied level? 4. How many valence electrons or outer shell electrons? 2. We come to germanium. What's the highest occupied level? 4. How many outer shell electrons or how many valence electrons? 4. Again, we do not want to get any more specific than that. This is just a general way that we can focus on the electrons that are a little bit more important than the others. Now, why do we want to just worry about the highest occupied, but in the previous two examples, we had to write them all out? Well, that gets to the third way that we're going to write or describe the location of electrons, and it's called electron dot notation, or just simply electron dots. Very simply, we're only going to show the electrons in the outer level. The other ones we don't care about. Instead of writing exponents, instead of drawing arrows, just put dots to represent the electrons. Here's the thing about this. We can never have more than 8. The reason being is the highest occupied level is going to be some combination of S's and P's, so we can never get more than 8. Basically, we just put dots around the element symbol. Now, what I've done here is two examples. One, this is just a generic symbol for whatever element X is, and we want to think of these 8 dots sort of going around 4 sides to the element symbol. More specifically, on the right-hand side here, the numbers represent the location for a specific number of electrons. For example, if I'm only going to have 1 electron in this symbol, and I want to put it sort of on the top right-hand side. If this element has 2 electrons in it, the second dot I want to put on the bottom left, or the left side bottom. 3, 4, and we see how this pattern alternates. So that's the location. Now, why is the location important? Can't I just put 8 dots around it or 6 dots? No, as we get into chapter 6 and bonding, we want it to be very specific, very organized, so that it's easy for us to identify what electrons are involved and where they're going. Now, this pattern here of the numbering 1 to 8, I basically show here on this screenshot. So if you look at this, if an element has only 1 electron in it, again, you see it sort of on the top right-hand side. If it has 2, they're in opposite spots. Right-hand top, left side bottom. 3, right side top, left side bottom, top side left. And you see how that pattern alternates. Again, this is very important that you are able to put these in the right location, in the right position. Otherwise, things will get very, very messy, and you'll have a tough time keeping track of this. All right, so the next thing what we'll do is we'll start looking at actual elements, how we write these, and the location that we will find them in.